Have you ever paused to consider the invisible architecture that breathes life into your computer, your phone, or even your smart home devices?
It's everywhere, isn't it?
Exactly. You tap an app, save document, or simply hit the power button, and it all just springs into action, almost like magic.
Mhm.
But what's truly, orchestrating that performance behind the scenes?
That's exactly our mission today on the deep dive. We're pulling back the curtain on operating systems, the OS, to really uncover their fundamental structures, the essential services they provide,
Uh-huh.
and how they act as the ultimate mediator between you, your software, and the hardware it all runs on. Think of this deep dive as, well, your shortcut to understanding the hidden world that makes modern computing possible, hopefully full of some surprising insights.
And for you, our listener, understanding this hidden world offers those incredible aha moments, right? It's about grasping the core principles that power everything from the device in your pocket to these vast unseen cloud servers. We'll try to make sense of the complexity without getting too bogged down. So let's unpack this. At its core, an operating system is like an incredibly helpful conductor for an orchestra, maybe. It provides essential services, and these seem to fall into two broad categories, those helping the user and those keeping the system itself running smoothly.
That's a great way to put it. The services that directly assist you are often the most visible ones. The obvious starting point is the user interface, or UI.
Right.
This is how you actually interact with your device. Most of us are super familiar with the graphical user interface, the GUI, that's your windows, icons, menus, all navigated with a mouse or trackpad.
Yeah, the standard stuff. Yeah.
Exactly. And it's come a long way, from early research back in the 70s, like Xerox, PR, to the intuitive visual experiences we have today with systems like macOS or Windows. But there's also the command line interface, or CLI. That's where you type text commands.
For the power users.
Often, yes. Think of it as a more direct way to talk to the computer. It offers really powerful control and efficiency for certain tasks. You see it a lot in Linux, Unix environments. And of course, for mobile devices, the touchscreen interface is king. Interaction through gestures right on the screen, like iOS or Android.
Okay, so that's how we interact. But the OS does more for us directly, doesn't it?
Oh, definitely. Beyond just the interface, the OS is constantly working for you. Think about program execution.
Getting apps running.
Precisely. Loading your apps into memory, getting them started, managing them while they run, and handling things when they finish normally or, crash.
Hopefully not too often.
We hope. It also controls all I/O operations, that's input and output. So whenever a program needs to read from your keyboard, write to a file, or talk to the network, it has to ask the OS.
Why does the OS need to be involved there?
Well, imagine the chaos. If every single program tried to directly control your printer or hard drive all at once. The OS steps in to manage access, ensuring efficiency and security. It prevents conflicts. And speaking of files, file system manipulation is another massive job. The OS manages everything about your files and folders. Creating, deleting, reading, writing, searching, organizing.
Permissions too, right? Making sure only I can see my stuff.
Absolutely crucial. It handles permissions, ensuring only authorized users or programs can access specific data.
Okay, so it helps our programs run. What about programs talking to each other? That sounds tricky.
It is, and that's where communication services come in. When different programs, or processes as they're technically called, need to exchange information, the OS facilitates it.
How does it do that?
There are two main ways. One is shared memory, where processes can read and write to a common shared section of memory. It's very fast for large amounts of data. The other is message passing. Here, the OS actually moves packets of information between processes. This works even if the processes are on different computers connected by a network. It's often better for smaller amounts of data or when processes aren't on the same machine.
Got it. Shared memory for speed, message passing for flexibility.
That's a good simplification, yeah. And finally, a less visible but vital service: error detection. The OS is like a vigilant guardian, constantly monitoring for problems in the CPU, memory, your storage devices, even issues within user programs.
And what happens if it finds something?
It depends on the severity. It might just log the error, or it might need to terminate a misbehaving program to protect the rest of the system. In really serious cases, it might have to halt the whole system to prevent, say, data corruption.
Wow. It's actually kind of amazing how many unseen things are happening just to keep our devices running smoothly, both for us and, as you said, for the system itself.
Exactly, because the OS isn't just helping us. It's also the master organizer for the system's own operations. This brings us to that second category. Services ensuring efficient system operation.
Right, keeping the machine itself happy.
Precisely. Think of resource allocation. You've got multiple apps open, right?
Hmm.
They're all competing for CPU time, for memory, maybe even for access to the printer or a USB drive.
Yeah, always.
The OS acts like a traffic controller. It decides who gets what resources and when. It uses clever scheduling routines, CPU scheduling algorithms to try and distribute these resources fairly and efficiently.
Makes sense. What else?
Then there's logging, sometimes called accounting. This is basically the OS keeping track of who used what resources and how much. It's not always about billing users, but it's incredibly valuable for system administrators trying to figure out performance issues or just understand how the system is being used.
Useful for troubleshooting.
Very much so. And finally, perhaps the most critical one, protection and security. This is absolutely paramount. The OS controls access to all system resources.
How does it do that?
It prevents one program from messing with another, either accidentally or maliciously. It stops programs from interfering with the OS itself. It handles user authentication, passwords. It protects sensitive areas of memory, defends against unauthorized access from outside, like over the network. It really is the digital bouncer for your system. As they say, a chain is only as strong as its weakest link, and the OS tries hard not to be that weak link.
It truly is.
Yeah.
All these services, some we see, some totally hidden, just weave together to create this robust framework that makes our digital world feel so seamless. Which makes you wonder, how do applications actually ask the OS for all these things?
That's the core mechanism. System calls. Think of them as the fundamental low-level language applications used to request services directly from the OS kernel.
So not the buttons I click, but something deeper.
Much deeper. For example, take something as simple as copying a file, like typing copysource.txt destination.txt at a command line. That single command triggers a whole cascade of system calls behind the scenes.
Like what?
Well, the application first needs to make system calls to get the file names you typed. Then it asks the OS to open the source file, maybe checking if it exists and if you have permission. Then it asks to create the destination file. Then it enters a loop. Read a chunk of data from the source file, that's a system call. Write that chunk to the destination file, another system call. It has to handle potential errors at each step, like running out of disk space.
Wow, that's long.
And finally, it makes calls to close both files. So dozens of these very specific requests for just one simple copy operation.
That really drives home the sheer volume of hidden work. But hang on, as a programmer, I rarely, if ever, write code that makes these direct system calls, do I?
You're absolutely right. Most programmers don't interact directly with system calls. Instead, they use something called an application programming interface, or API.
Okay, I've heard of APIs.
Right, APIs like the Windows API or the PO6 API, which is common on Linux and UNIX-like systems, or the Java API. They provide a set of functions that are much more convenient and programmer-friendly. They act as a layer above the raw system calls.
So the API function hides the complexity.
Exactly. When you call an API function, say, to read from a file, that function, behind the scenes, makes the necessary, often more complex system calls for you.
Ah, okay. That makes sense. Why do it that way?
Two main reasons. Ease of use, definitely, but also portability. If you write your program using a standard API like POC/DX, in theory, you can recompile it and run it on any operating system that supports that PO6 API without changing your code much. The API layer handles the translation to the specific system calls of that OS.
So how does that translation happen, the API call to the system call?
That's where the runtime environment, or RTE, comes in. It's sort of a support library linked with your application. When your application calls an API function, the RTE intercepts that call. It then looks up the corresponding system call number for the current operating system, often using a special table, sets up any parameters needed, and then makes the actual jump into the OS kernel to execute the system call.
Like a hidden interpreter.
That's a great way to think about it. It acts as the crucial bridge, translating the programmer-friendly API request into the low-level language the OS kernel understands. And usually, this whole process is completely transparent to the programmer.
Which is definitely a good thing. So system calls are like the verbs the OS understands.
Yeah.
Are there different categories, like different types of actions?
Yes, definitely. We can group system calls into several major categories based on what they do. First, there's process control.
Starting and stopping programs.
Exactly. Creating new processes, terminating them, loading code, executing it, waiting for processes to finish, getting or setting their attributes, all that management stuff. Then there's file management. This covers pretty much everything you can do with files. Create, delete, open, close, read data, write data, reposition within a file, get or set file attributes like permissions.
Makes sense.
Third is device management. This is similar to file management, actually. Many systems, especially UNIX-like ones, treat devices almost like files. So you have calls to request access to a device, release it, read from it, write to it, and so on. Think printers, USB drives, terminals.
Okay, what else?
Fourth, information maintenance. These calls let programs get information about the system itself. Things like the current time and date, the OS version, how much memory is free, system performance data. It also includes calls helpful for debugging, like dumping memory contents or tracing program execution. Fifth is communication. We touched on this earlier with shared memory and message passing. The system calls here are for creating or deleting communication channels between processes, sending or receiving messages, or setting up and attaching to shared memory regions.
Right, for programs talking to each other.
Precisely. And finally, number 6 is protection. These are the calls related to controlling access, setting permissions on files or other resources, getting current permissions, allowing or denying access for specific users.
It's really fascinating how these underlying calls form the absolute basic language the OS uses to talk to applications, even though we usually interact with things that feel much higher level, like those system services.
Exactly. And that's a perfect transition. Beyond those raw fundamental system calls, the OS also provides a whole suite of ready-made system services, sometimes called utilities. These are typically separate programs built using the system calls, designed for user convenience.
So these are things I might run directly.
Often, yes. Think about file management utilities programs to copy, move, rename, delete, or print files. That graphical file explorer you use, that's a system service using file management system calls underneath.
Okay.
Or status information utilities, programs that show you the date and time, how much disk space is free, network status, system performance monitors like Task Manager or TOP. Even debugging tools often fall into this category. Then you have file modification tools like text editors or commands to search for patterns in files.
Compilers and things like that.
Right. Programming language support is a big one. Compilers, assemblers, debuggers, interpreters, these are crucial services for developers provided by or alongside the OS. And when you actually want to run a compiled program loading and execution services, the loaders will talk more about handle getting it into memory and starting it.
And things like web browsers.
Absolutely. Communication services like web browsers, email clients, tools for remote login or transferring files, these are essential system services today, even if they feel like separate applications.
And sometimes things just run without me starting them.
Yes, those are background services, often called daemons in the UNAX world, or just services in Windows. These are programs that run quietly in the background, waiting to do something. Like a network service listening for incoming connections, a process scheduler managing tasks, or a print server handling your print jobs. These utilities and services are what make the raw power of the OS accessible and genuinely useful.
It's almost like a magic trick, the way the OS just seamlessly prepares and runs our programs. So you mentioned loaders. How does a program actually get ready to execute? What's that journey like, say, from the code a programmer writes to a running application?
It's quite a multi-step dance, involving key players called linkers and loaders. It starts, obviously, with the source code written by the programmer.
Right.
First, a compiler takes that human-readable source code and translates it into machine-readable object files. These are compiled pieces, but they aren't quite runnable yet. They might be missing connections to other code pieces or library functions.
Okay, so compiled but not complete.
Exactly. Next, the linker comes in. Its job is to take one or more of these object files, perhaps combine them with code from standard libraries like math functions or input-output routines, and resolve all the cross-references between them. The output of the linker is a single, complete executable file. Think of it as assembling all the different parts of a machine into one functional unit.
And that's the file I double-click.
Usually, yes, that's the file ready to be run. Finally, when you do launch it, the loader, which is part of the operating system, takes that executable file from your disk, places it into the computer's main memory, RAM, sets everything up just right, and tells the CPU to start executing its instructions.
Is all of the code always loaded at once? Programs can be huge.
Good question. Not always. A common optimization, especially in modern systems, is dynamic linking. Instead of the linker bundling everything into the executable, some parts, especially common library functions used by many programs like DLLs in Windows or shared objects in Linux, are kept separate. The loader only brings them into memory when the program actually needs them during runtime.
So it saves memory.
Exactly. It saves memory because the library code is only loaded once and can be shared by multiple running programs. It also means executables can be smaller. This whole compile link load process happens every single time you launch an application, mostly invisibly.
That intricate process makes me circle back to a previous thought. If this happens every time, why can't a program compiled for Windows just magically run on Linux or macOS or vice versa? It still seems like it should be simpler than it is.
It's a really common and perfectly logical question, but the core issue goes back to those fundamental differences we've been discussing. Each operating system has its own unique set of system calls.
The basic language is different.
Precisely. And not only that, they often expect programs to be packaged in a specific binary file format like PE format for Windows, ELF for Linux, Mach-O for macOS. The way a program asks the OS to, say, create a window or allocate memory or even just exit is fundamentally different. The instructions might even be different if they're compiled for different CPU architectures like Intel by 86 versus ARM.
So it's not just one thing, it's multiple layers of incompatibility.
Exactly. System call differences, binary format differences, potentially even CPU instruction set differences. It all adds up.
Are there ways around this? How do we get cross-platform apps at all?
There are several strategies. One is using interpreted languages like Python or Ruby. The code itself isn't compiled to machine code. Instead, an interpreter program reads the code line by line and translates it into actions, making the necessary native OS calls on whatever system it's running on. Performance can be a trade-off, though.
Okay.
Another approach is virtual machines. Think Java with its Java Virtual Machine, JVM, or Android apps with the Android Runtime, RET. You compile your code to an intermediate bytecode, and the virtual machine, which is ported to each specific OS, executes that bytecode. The dream is write once, run anywhere.
Does it work?
Often, yes, but sometimes with nuances or performance considerations. A third way is to write code using standardized APIs, like PO6. You still have to compile the code separately for each target OS and architecture, but the source code itself is largely portable. The compiler generates the OS-specific executable using the correct system calls.
But even with these, it's still a challenge.
Absolutely. Getting an application like, say, Firefox or a big Office suite to run natively and efficiently across Windows, macOS, Linux, and maybe even mobile platforms requires a huge amount of dedicated engineering effort to handle all those underlying differences. It really underpins the whole software ecosystem we see today.
It truly does. It's a massive undertaking. So, knowing all this complexity, what actually goes into building an operating system from the ground up? What are the goals?
Well, designing an OS is this incredible balancing act. You have these high-level goals. From the user's perspective, you want it to be convenient, easy to learn, reliable, safe, and fast. Pretty straightforward, right?
That was good to me.
But then there are the system goals from the perspective of the developers building and maintaining the OS. They want it to be easy to design, implement, and maintain, flexible, reliable, error-free, and efficient.
And those two sets of goals aren't always perfectly aligned, I imagine.
Exactly. Sometimes making something super easy for the user makes it incredibly complex to implement efficiently and reliably underneath. A crucial design principle that helps manage this complexity is the separation of mechanisms and policies.
Okay, what's the difference?
A mechanism is how something is done. For example, the OS might have a timer mechanism to limit how long any one program can run before being interrupted. That's the how. The policy is what will actually be done using that mechanism, for instance, deciding how long that timer should be set for different types of programs.
Ah, so you can change the policy without rewriting the core mechanism.
Precisely. It gives you flexibility. You can tune the system's behavior by adjusting policies without having to redesign the fundamental building blocks. Different OS structures embody this separation to different degrees.
And how are OCs actually implemented these days? Is it still super low-level stuff?
Historically, yes, a lot was done in assembly language, very close to the hardware. But that's incredibly difficult and time-consuming. Today, most operating systems, including the kernels of Windows, Linux, macOS, are primarily written in higher-level languages, predominantly C, with some C++ and critical parts still in assembly. Frameworks might use Java, like in Android.
Why the shift?
Advantages are huge. It's much faster to write code. The code is usually more compact, easier to understand and debug, and crucially, much easier to port to different hardware architectures.
Is there a performance hit compared to pure assembly?
There used to be a bigger concern about that reduced speed, increased storage, but honestly, with modern optimizing compilers and processor designs, that difference is often minimal for most parts of the OS. Major performance gains today usually come from using smarter data structures and algorithms, not just from hand-tuning assembly code, except maybe for a few absolutely critical performance-sensitive routines.
So OS design is really this creative, evolving field, constantly balancing ideals with very practical performance realities. How are all these different pieces, the services, the mechanisms, actually organized within the OS itself? What are the main structures?
That gets us into operating system structure, how the components are arranged inside the kernel. The, let's say, simplest traditional approach is the monolithic structure.
Meaning everything is in one big block.
Pretty much. All the core OS functionality, process management, memory management, file systems, device drivers is compiled into a single large binary executable. Everything runs in the same kernel address space. The original UNIX was largely monolithic, and Linux is a prime modern example, though it has evolved.
What are the pros and cons?
Pro. It's generally very high performance because components can directly call each other very efficiently. Con. It can be incredibly complex to develop, debug, and especially extend. A bug in one driver could potentially crash the entire system.
Okay, so what's an alternative?
Another classic idea is the layered approach. Here, the OS is broken down into a number of distinct layers, stacked like a cake. Layer 0 might be the hardware. Layer 1 deals with memory management, Layer 2 with process scheduling, and so on, up to the user interface at the highest layer. Each layer can only use functions provided by the layers directly below it.
Sounds organized.
It simplifies design and debugging in theory, because you only need to worry about the layer below you, but it's actually quite difficult to define the layers cleanly in practice. And the big drawback is performance. A request might have to pass through many layers, adding overhead at each step. So purely layered systems are pretty weak today.
So monolithic is fast but complex. Layered is organized but potentially slow. What else?
The microkernel approach is almost the philosophical opposite of monolithic. The idea here is to remove as much as possible from the kernel itself. Non-essential components, things like file systems, device drivers, networking stacks, are implemented as separate user-level programs or servers.
So the kernel becomes really small.
Exactly. The microkernel itself is tiny, primarily responsible for just the absolute basics. Managing processes or threads, handling memory, and facilitating communication between those user-level servers, usually through message passing.
What's the benefit of that?
Easier to extend the OS, just add a new server process. Easier to port to new hardware, only the tiny microkernel needs significant changes. Potentially more reliable and secure if a device driver crashes, it only takes down that one server process, not the whole OS. Mach, which forms part of the Darwin kernel in macOS and iOS, has microkernel roots. Q and X, used in embedded systems, is another example.
That's great. Is there a catch?
Performance. That communication between user-level servers via message passing through the microkernel adds overhead compared to direct function calls within a monolithic kernel. Copying messages back and forth takes time. Early versions of Windows NT had some performance challenges related to its microkernel-inspired design, for instance.
Okay, so trade-offs everywhere. Is there a middle ground?
Yes, and that's where most modern systems actually live. Many use modules, often called loadable kernel modules or LKMs. You have a core kernel, maybe somewhat monolithic, but many services like specific file systems, device drivers, networking protocols are built as separate modules that can be loaded into the kernel dynamically, either at boot time or even while the system is running.
Like plugging in a new piece of hardware.
Exactly. You plug in a USB drive, the kernel loads the appropriate USB storage driver module. Linux, macOS, Solaris, Windows, they all make extensive use of modules. It offers much of the flexibility of a microkernel, easy to add functionality, but often with better performance because once loaded, the module runs in kernel space and can communicate more directly without the message passing overhead.
So the reality is messy.
The reality is hybrid systems. Pretty much every major OS today mixes and matches these approaches to get the best blend of performance, flexibility, security, and usability.
Can you give some examples?
Sure, Linux is fundamentally monolithic but heavily modular. Windows is largely monolithic internally, but incorporates concepts from microkernels, like subsystems, has distinct personalities, and uses loadable drivers extensively. A fascinating recent example is the Windows Subsystem for Linux, WSL. It lets you run native Linux command line tools and applications directly on Windows. It does this through some clever translation layers that map Linux system calls to equivalent Windows calls, running the Linux binaries in lightweight Pico processes.
Wow.
Or look at macOS and iOS. They share the underlying Darwin kernel. Darwin itself is a hybrid. It uses the Mach microkernel at its core, but incorporates a large amount of code from the BSD UNIX kernel, running much of it within the same address space as Mach to improve performance over a pure microkernel. It uses kernel extensions, kexts, which are like modules, so it's layered, uses microkernel concepts, includes monolithic components, and is modular. Android is another great example of a hybrid layered system. It runs on top of a modified Linux kernel, modified for things like power management specific to mobile devices, and a special communication mechanism called binder IPC. Above that, you have hardware abstraction layers, HALs, native libraries, often written in C++, the Android Runtime, ART, for running apps, and then the application framework and the apps themselves. It's designed for portability across vastly different hardware.
So it's clear there's no single best structure. It's all about trade-offs tailored to the system's goals. Now, once an OS is designed and maybe compiled, how does it actually get onto a machine and start running in the first place?
Right, that involves operating system generation and the system boot process. OS generation is basically about configuring and building the OS binary itself. For end users installing, say, Ubuntu or Windows, you typically download a pre-built installer image, like an ISO file, designed for general hardware.
But for developers or custom systems,
If you're building a Linux kernel from source, for example, you'd configure it first, choosing which drivers and features to include, often using a tool like make menu config. Then you compile the source code, install the modules, make modules install, and install the kernel itself, make install. The goal is to create a kernel image tailored to the specific needs or hardware.
okay, so the OS is built and installed. How does the computer actually start it when I press the power button?
That's the system boot process. It all begins with a small piece of code stored in firmware on the motherboard, historically, the BIOS, more recently, UEFI. This firmware contains the initial bootstrap program, or bootloader.
Its only job is to start the OS.
Pretty much its main job. When you power on, the firmware runs first. It performs some basic hardware checks, power on self-test or post-at. Then the bootstrap loader's task is to find the actual operating system kernel on a storage device, like your hard drive or SSD, and load it into memory.
Is it always that simple?
Often it's multi-stage. The firmware bootloader might be very small and just load a slightly larger, more capable bootloader from a special area on the disk, the boot block. This second stage loader, like GRUB, which is common on Linux systems, might then present you with a menu, if you have multiple OCs installed, before finally loading the selected OS kernel. UEFI is generally more sophisticated and can handle more of this directly than the older BIOS system.
Okay, so the bootloader finds the kernel and loads it. Then what?
The kernel image gets loaded into memory. Often it's compressed, so the first thing it does is decompress itself. It might set up a temporary RAM-based file system, initramps in Linux, to load essential drivers needed to access the real root file system on disk. Once it can access the main file system, it mounts it, initializes various subsystems, and starts the first main user space process, often called init or systemed on modern Linux. This process then proceeds to start up all the other system services and eventually presents you with the login screen or graphical desktop.
It's quite an intricate sequence just to get things going.
It really is. And it's similar on mobile devices like Android, though the specifics of the bootloaders and initial processes might differ. There are also usually ways to boot into special modes, like recovery or single user mode, for diagnostics or repairs if the normal boot process fails.
That's a truly complex dance. Now, even with all this careful design and booting, systems aren't perfect. Errors happen. That must mean operating system debugging is a crucial ongoing thing.
Absolutely essential. Debugging isn't just about fixing outright errors or bugs, though that's a big part. It also involves performance analysis and tuning, finding bottlenecks that slow the system down.
So what happens when something does go wrong, like an application crashes?
If a user program crashes, the OS typically steps in. It might write error information to a system log file. It might also generate a core dump, which is essentially a snapshot of the program's memory contents at the time of the crash. Developers can then analyze this dump with a debugger tool to figure out what went wrong.
And if the OS itself crashes, the dreaded blue screen of death.
Kernel failures, or crashes, are obviously more serious. When the kernel detects an unrecoverable internal error, it will usually try to record as much information as possible about the state of the system into a log and generate a crash dump, a snapshot of the kernel's memory. This dump often gets written to a special pre-allocated area on disk because the file systems might be unstable at that point.
Why is kernel debugging harder?
Several reasons. The kernel is incredibly complex, it interacts directly with hardware, and if it crashes, you can't just rely on normal user-level debugging tools. Plus, the act of writing the crash dump itself has to be extremely careful not to corrupt the storage. After rebooting, the system can analyze the crash dump file.
Okay, so that's crashes. What about finding those performance bottlenecks you mentioned?
For that, OCs rely heavily on performance monitoring. One basic technique is using counters. The OS keeps track of various activities, how many system calls are made, how much network traffic is flowing, how many disk operations occur, CPU usage per process, etc.
And tools read these counters.
Exactly. Tools like Windows Task Manager or Peace and Top on Linux query these counters to give you a real-time view of what the system and individual processes are doing. On Linux, much of this data is accessible through a special pseudo file system called proc.
What if counters aren't enough?
Then you move to tracing. Tracing tools record detailed information about specific events as they happen. For example, Strace on Linux can show you every single system call a particular program makes, along with its arguments and return values. GDB is a source-level debugger. Perf offers powerful performance analysis capabilities. TCP dump lets you capture raw network packets.
Sounds powerful, but maybe complex.
It can be, but there's some really cutting-edge stuff happening here too, especially in the Linux world with technologies like eBPF, Extended Berkeley Packet Filter, and tools built on it like the BCC BPF compiler collection.
Okay, what do they do?
eBPF allows developers to write small, safe programs that can be dynamically loaded directly into the running kernel to collect incredibly detailed tracing and performance data. Think of them as custom probes you can insert almost anywhere. BCC provides a user-friendly front end, often using Python, to write and use these eBPF programs.
You can modify the running kernel safely.
Yes, that's the key. eBPF programs go through a strict verification process before being loaded to ensure they won't crack the kernel or introduce security holes. This means tools based on BCC and eBPF can be safely used on live production systems. System administrators use them to diagnose subtle performance issues, track down resource leaks, or even monitor for security exploits in real time without needing to reboot or disrupt services. Tools like OpenSnoop can show you every file being opened. Disk Snoop shows disk latency. It's incredibly powerful for understanding system behavior at a very fine grain.
Wow, that's amazing. This whole discussion really underscores the constant, ongoing effort required to refine, stabilize, and optimize these incredibly complex systems, often while they're running critical tasks.
Absolutely. So we've taken quite a journey today. We started with the fundamental services an operating system provides for the user and for itself. We looked at the interfaces, how programs actually talk to the OS via system calls and APIs. We dove into the different ways OCs can be structured, monolithic, layered, microkernel modules, and the hybrid reality. And we touched on how they're built, booted, and the crucial process of debugging and performance tuning. It's a testament to some incredible engineering, really.
It really is. And hopefully for you listening, you now have a much deeper appreciation for that invisible architecture powering your digital world. From that simple click of a mouse or tap on a screen to the complex dance of software and hardware on servers far away, it highlights the ingenuity that lets us interact with such complexity with what feels like, well, ease.
And maybe a final thought to leave you with. Looking ahead, we see hardware constantly evolving, think quantum computing on the horizon, AI accelerators becoming standard, the explosion of tiny edge devices everywhere. What new challenges, what new structural innovations do you think operating systems will need to embrace next? How will they stay efficient, secure, and user-friendly in the face of such change? It's a fascinating question for the future of computing.
A truly thought-provoking question to ponder. Thank you so much for joining us on this deep dive into operating system structures. Keep exploring, keep learning, and keep asking questions about the technology that shapes our world.